Started, I want to acknowledge my kind of co-investigators, Dan Line and Dr. Jack Kirky Fox. They really do all the heavy lifting on the modeling work that I'm going to show you. A lot of technical analysis from these guys. And also you'll see a lot of logos at the bottom of the screen. We have worked with a number of partners on some of the work that I'm going to show you on the Neuse River Basin, and that work was funded by the UNC the NC Policy Collaboratory that's based out of UNC, North Carolina. So I do want to give a call out on those people and organizations before we get started. As you probably know, we've experienced some very severe events in about a 20-year period. We had three major storms that cost billions of dollars in damage, resulted in loss of life. A lot of homes were damaged, businesses, and many rescues. And a big part of the problem also was impacts to some of our transportation system, which really roads were washed out, bridges were overtopped, and we had major interstates that were closed for over a week in the case of some of these storms. So pretty much creates a situation of paralysis. So that's a real initiative for trying to figure out ways we can address it. I work with both North Carolina Sea Grant and the NC State Bio and Ag Engineering Department, and we have a long history here at the university of working with ecological restoration and forest systems and agriculture. So one of the questions we've been asking is how these kind of natural systems could be used maybe to help mitigate flooding. So we wanted to kind of take a deeper dive into that. And that's what we've been working on for the last several years here, is kind of experimenting with that concept. And why we want to look towards these kind of nature-based solutions is because unlike big impounded reservoirs or dikes and levees, these types of systems can also provide environmental as well as economic benefits, especially related to water quality and even habitats that can not only provide for animals, but would provide economic potential for our state as well. A newer concept we've been looking at in the last few years is this idea of water farming. This is something that has been done in areas of Florida where they used an engineered system where they build a kind of berm to contain water on that area during major flow events. This is intended to either reduce downstream flooding or provide water quality impacts. This is one in South Florida that's really focused more on water quality impacts. So the berm or terrace that you build around the property is something low. You don't want very high embankments. So this is about 5 feet limit on that. And you would have to install structures at the outlet of this to kind of hold the water back and then release it slowly. Again, these systems don't hold water in every rainfall. They're mostly intended to operate in large events if they're intended for flood mitigation purposes. So one of the research questions we've had then is how can we use these systems such as wetland restoration, stream restoration, planting more trees, farming, doing the storage of water on farms and areas. How could this mitigate flooding, and what would be some other ancillary benefits for that? And our approach to do that, kind of look at that, answer that question, is to first identify opportunity. Where can we put these things out on the landscape? And then second, we do a lot of modeling of hydrology to determine what type of flow reductions, in particular when we get a big event, what kind of peak flow reductions could we achieve? We've also done modeling of water quality benefits, and we've done a lot of work to estimate kind of some cost and benefits of this. And this is something we want to expand on more. Initially, we were funded by the Environmental Defense Fund to do look at a couple creeks, small creeks in Goldsboro, North Carolina. One of those is called Big Ditch. It has about a 3 square mile watershed. It's a very developed watershed, about 93% developed with lots of impervious cover. There's that watershed. And this channel has been very modified. It's been straightened, armored with concrete and other materials. And a lot of development has occurred within the 100-year floodplain of this creek. It has numerous road crossings, and many of those are undersized. In fact, they overtop in about a 10-year storm. So we looked at how both kind of the typical engineering approach to how we would address flooding in this area and the natural infrastructure type approach for dealing with flooding along this creek. I'm going to kind of skip to the chase and get to the summary of what we found. But what we did is we ended up kind of combining engineering, kind of gray infrastructure with the green infrastructure measures, and we did some optimization. We enlarged 7 crossings on the stream. These are the ones in gray. So we found we had undersized bridges and pipes. We enlarged those to convey more water. We removed what we call redundant crossings. They had a little road, every single little road went across the creek in these relatively small neighborhoods. So we eliminated those, and that would provide an opportunity to then expand the floodplain for the creek. So we modified the creek to have more of a smaller channel that would convey like a mean annual high flow and a floodplain that was about 6 times wider than this channel. So providing more floodway capacity for the stream. And what we saw is that this kind of combined approach would give us benefits even in the 500-year storm event. This is results from the hydraulic modeling of this Big Ditch Creek. And the blue line here shows the water surface profile of that storm in the existing condition. And you can see where you have small undersized bridges and culverts, you get a backwater effect where the water rises up and is impounding areas upstream. This actually goes upstream to downstream here. And then the red line shows with all those measures of removing redundant, expanding the other crossings, and adding that floodway along with the stream restoration type project. So you see substantial reductions in that water surface and getting rid of that kind of backwater in areas. We also looked at the inundation, or kind of the footprint of flooding. The blue shows existing for the 100-year storm, and then the red shows this new, what we call the resilient approach, combining that. So what we found is that both floodplain restoration and crossing modifications were necessary, but you also have to buy out structures, which is something we've been doing a lot of. So it's no one single silver bullet to fix flooding along this small creek. Rather, it's this combined approach of doing the buyouts, expanding the floodway, and improving our kind of gray infrastructure as well. And I think that's the case we'll see in a lot of watersheds around the state, is that we have to do multiple things to find a solution. The second creek we looked at in Goldsboro was Stony Creek. This one's a little different than Big Ditch. It is a larger watershed of 31 square miles. It's about 43% developed and has 30% ag. And most of the ag land is concentrated in the upper portion of this watershed, with the urban areas downstream. We looked at kind of 3 modeling scenarios in this watershed where we would do kind of some of that water farming or storage and retention. We looked at reforestation, planting trees in a lot of it, and then we looked at the combination of those two things to see what type of flood mitigation benefits we could get. So for storage and retention, that's the kind of blue hatched areas here in the watershed, were areas that we could build about a 2-foot tall berm around existing ag and forest land and to hold water temporarily. And that was about 10% of the watershed we found available that might be appropriate for that. For reforestation, we did converting most of the cropland there in the basin to trees instead. So that would be kind of, it's more a theoretical. It's not likely we would get all that land, but we wanted to see what kind of flow reductions we could get. And then we combined the measures together. And then we looked at different return interval storms. We looked at the peak flows for those. So the blue shows the existing flows for those storms. And then we looked at those scenarios where it's storage, retention, reforestation, and combine. And we see when we combine the practices, we could get about a 28% reduction in peak flow for the 500-year storm event. And good reductions you see in the 100 as well. So we were very encouraged by these results and wanted to look a little closer. So that all led into a project looking at the full Middle Neuse Basin, which I'm showing that full Middle Neuse going down to the point of Kinston here. We did not include the upper Neuse Basin because this all drains through Falls Lake, so that's already regulating flows in that portion of the basin. So we wanted to focus on this portion downstream of Falls to Kinston. And our approach for this was again to identify opportunity for natural infrastructure in this area, then to model the hydrology benefits, model hydrology before, without it, and with those natural infrastructure measures in place, estimate reductions, and then extrapolate results back to the full basin. So the way we did that is it would be too difficult to do the whole basin. So we focused in on these three sub-basins, the Little River, Nahunta Swamp, and Bear Creek, because these are relatively small sub-watersheds. They also, each of these have a USGS flow gauging station, but at the downstream end of that. So we modeled these basins in a great detail and then used the results of that to kind of then extrapolate to the full Middle Neuse Basin. So as far as identifying opportunity, we kind of did the typical approach where you take a lot of GIS layers of soils, land slopes, land use, and overlaid all those and said, voila, here's where natural infrastructure can go. And I've seen a lot of work like that from others. But then we did something different where we went out and to those subbasins and we visited 241 of those sites we identified, and we said, is this really a good site for a wetland or for water farming or for reforestation? And we found that there were a lot of discrepancies from that kind of mapping process to reality on the ground. So then we went back to the drawing board and really refined our GIS analysis. So for example, with water farming, we limited slope to 1%. We had to put buffers on roads. We buffered around all structures like buildings, hog farms, houses, whatever structure. We put 100-foot buffers around any lagoons that we identified, and we removed very small parcels of 400 acres or less. And then we kind of zoomed in on several of the sites identified and we said, all right, what would a water farm look like on the site? So we got the digital elevation model for these sites, which is kind of very detailed topography. And we said, where would we need berm, which is shown in red? So that's at the kind of lower extremities, the downstream edges of this farm. And then each of these two examples. And then we said, where do we need a water control structure? And that's each of these where there's a ditch outlet that's draining that farm, where to put those. And so with this data, we could then get some numbers about volume and length of berm needed. We could calculate the amount of water stored on that acreage of farm. And that also helped us with the costing analysis of water farming, where we could develop relationships based on per acre of how much earthwork would be needed, how many structures, and then how much water storage, kind of acre foot per acre of land we could store. We also generated some concept designs for the farm, the research farm at Cherry Station in eastern North Carolina, and developed some renderings that we could be able to show farmers and large landowners what this system would look like. And so basically the most appropriate land, again, was land that's not already flooded. So we kind of excluded areas that were already in the 500-year floodplain, no structures or roads, and slopes less than about 1 to 1.1 1.1%. And we isolated down to contiguous parcels that were at least 20 acres in size. So we had a kind of substantial area to store water. So this is the Nahunta Basin, and in yellow, we see the areas that were initially identified through our GIS process, and then the red areas are the ones that we really boiled down to that these are the truly more appropriate sites for that. So you can see a big difference in that. So I really want to point out that it's very important that we refine our kind of opportunity analysis again, and some of these numbers that have been put out by other groups to kind of say, well, let's look more closely at where this is appropriate. So the yellow areas here show Bear Creek, where the opportunity we found, and here is Nahunta. These are the areas we found appropriate for water farming. And then we extrapolated what we learned from those basins out to the full basin. You'll see that in Little River and many of these upper basins, we had zero opportunity for water farming, and that was really because there's too much developed land and the slopes are too steep. So we really don't have opportunity for that. You could try to put it on steeper slopes, but you'd have a lot more berms closer together and the cost would really go up and some of the risk may go up as well. So we found about 5% in Nahunta and Bear Creek were appropriate, and only about 1.1% of the land in the full Middle Neuse was appropriate for water farming. So then we looked at wetland areas. Typical wetland restoration in eastern North Carolina, it really involves plugging ditches, kind of grading some microtopography to get kind of variable water levels, and then planting. But this type of approach would not work for flood mitigation because these areas are already usually full of water by the time a major storm comes. There's no real storage potential to help uh, provide detention of water to prevent flooding downstream. So we need some type of storage element that would be held by an earthen berm and would have an outlet structure that's going to regulate flows out of that. We got to have that storage element. So again, we looked at what would that look like on farm land, and this is on the Cherry Farm again, where we took an existing ag ditch and showed it excavating that ag ditch out, kind of removing a portion of that farmland out of farming, converting it to this wetland. And so the wetland area would have low water in it, but it would have an earthen berm. This is the berm here that would be holding back water in bigger storms. So this pipe would be sized such that it does that detention element, temporary storage of water in large events. So we know we needed to site the wetland in an area where it had enough watershed, water draining to it, that it was going to give that benefit. So we isolated to looking at the ditches that drain rural land that had at least 35 acres of land. And then we sized we sized our wetland to be about 10% the size of the watershed area that it was draining. So why is that 10%? Well, what we did is we kind of modeled the flows in different storm return intervals, varying the size of the wetland to catchment ratio. And what we found is that about 10%, you see this kind of diminishing returns where things really, the benefit of excavating bigger and bigger was not to your advantage because this kind of line flattens out. But at about 10%, we could get almost an 80% reduction in the peak flow for the 100-year event. If we looked at the 500-year event, this 10% sizing ratio would give us a little over 40% reduction in peak flow. So we felt that was a kind of good target. We had to, of course, make some assumptions about those watersheds for that analysis. So then looking at our Bear Creek watershed, the red areas show all the wetlands we've found sites for, and the blue shows the watershed that would drain to that. Because again, you want to have an area of land draining to that wetland that you're going to be able to hold and store that flow temporarily. And here's the same thing for the Nahunta Basin. And what we found is about We found a little bit of opportunity for this in Little River, but less, again, because of slope limitations and land use limitations. In Nahunta, we found about 12% of the basin, that's the area controlled, the watersheds, and Bear Creek about 21% watershed control. So that's pretty substantial opportunity, and about 5.7% in the full basin. You can see that the opportunities are higher again in the lower portion of the Middle Neuse where slopes are flatter and we have more rural land available. We looked at reforestation, where we would convert low productivity cropland or low productivity soil areas to forest. We did not want to focus in on the most productive areas for crops because we knew that wouldn't be a desirable change. So again, we use this National Commodity Crop Index and isolated to areas with a score of less than 0.33. And so for Bear Creek, we see we had a lot of opportunity kind of closer down to the lower part of that basin along the creek. In the Hunta Swamp, we did not have much area that ranked as low productivity cropland, so not much opportunity in that basin. And we look in the Little River, this is something we saw in the upper part of the Middle Neuse that we do have more opportunity for this reforestation conversion. So we had a reasonable amount of opportunity there. So Little River was about 6.5% of that basin, only 1.8 in the Hunta, about 10.6% of Bear Creek, and 8.4%, which is pretty good percentage for the full Middle Neuse of opportunity. And you see that is distributed more throughout the basin, unlike wetlands and water farming. So how do we evaluate that? So for each of the three study subwatersheds, Bear, Nahunta, and Little River, we developed a detailed HEC HMS hydrologic model and then calibrated that model to the USGS flow gauge data that we had. So here's the model calibrations for Matthew, Hurricane Matthew. That was the storm we used for Nahunta and Little River. For Bear Creek, we had to use Hurricane Floyd, and the blue line shows the observed, and the modeled is in red, and you can see very good agreement for our models that we developed. We were able to get good calibration on these storms. So then we added those natural infrastructure practices to each of these basins. And we did different techniques with creating kind of reservoir storage, adjusting curve numbers to achieve that simulation of each of those areas. So these were put at each location in the subbasin where we had an opportunity in that basin. And so then we compared the discharge to existing condition of the various scenarios that we had. So in other words, here's our calibrated existing condition for Nahunta Swamp. Here's where the USGS outlet is for that basin. And here we have reforestation in red, then water farming in green, wetlands in purple, and the combining water farming and wetland in that basin. We can see the peak flow reductions are highest for that combined approach of 13.6% peak flow reduction for Nahunta. And here's the total percentage of those practices. And that would equate to about a 0.4 foot drop in the water surface elevation at that outlet of Nahunta Swamp. If we look at the 100-year storm, we actually looked at several return interval storms as well as, because this is for Hurricane Matthew, that would be the reduction. We looked at several return interval storms, and we see that the footprint change in flooding, which it goes from this hatched area is the 100-year inundated area, and the blue is the change with natural infrastructure. We don't get a big change in the footprint, but it's more of just kind of lowering that water level. And that's because in these very big storms, the typical formation of our streams is that we have a channel that has a floodplain, and when we get in bigger storms, the stream is out of that area out onto the floodplain. So we're not talking about getting rid of flooding, we're only talking about lowering those water levels a bit. And we see similar reductions though even for the 500-year storm. So we had good reductions there. We look at Bear Creek Again, our kind of storm of focus there was Floyd because of the gauge data. Here's our percentages of the practices. And again, the combined approach is the most reduction at about 21.8%. And this is water farming, wetland, and reforestation for this combined approach. So you can see very good reductions. And this is a lot because we had very high wetland opportunity in Bear Creek. And this would equate to about a 1 foot drop in a Hurricane Floyd event at the outlet of that watershed. If we look at the other return interval storms, we can see some reduction in flooding footprint for the 100-year storm, and about a 0.8 foot drop for the 100-year storm. So you actually get more drop in water level for that Hurricane Floyd event than you do for the 500. And you can see the 500 goes up, and that has a lot to do with the kind of sizing structure of the natural infrastructure. Looking at Bear Creek in detail, we found that the reductions are highly variable throughout the watershed. And that has to do with kind of timing of flow as well as the density of that natural infrastructure in there. And so we have some areas at this location 1 at 6 and 7 where we're reaching over 30, almost 50% reductions in peak flow at these locations. So that was kind of very encouraging, but very much the reduction has to do with the location that you're looking at and how much the density of that natural infrastructure. And so in some areas of the watershed, we had greater than a foot reduction in water surface levels. So we see that the reductions kind of in the upper part of this sub-watershed are even greater than what you would see at the outlet. And this was for the 100-year storm here. So then we went about how we're going to extrapolate what we learned in these 3 subbasins to the bigger basin. And so what we did is we looked at 3 kind of, we modeled peak flows for 3 scenarios and at 3 levels of implementation for Bear and Nahunta. The 3 scenarios were water farming, wetland, and then the combination of those. And we looked at the implementation levels of doing only 25% of what we identified, 50, and everything we identified. And we used that to get these regression equations from those data points and we got, pretty good relationships here that we could take then based on the area of implementation or affected in that for water farming and wetland, what would be the peak discharge reduction? And so that's what we used to extrapolate. And so we went in and modified the this discharges that were coming out of each subbasin based on that, how much opportunity you had in using those relationships, and a more simple procedure for the reforestation as well. So combining that on top. So again, here's the kind of full implementation for the basin, the levels, and then this is the resulting peak flow reductions we saw for each sub watershed. And so the very highest levels down here, Bear Creek happens to have the highest reductions of any watershed, sub watershed in the sub-Neuse, and very low reductions in the upper percent, just because there was not much opportunity for those practices there. There was some reforestation, but you just don't get quite the peak flow reductions with reforestation that you see with wetland and water farming, which wetland has the highest reductions of the 3 practices we looked at. So then we looked at the outlet. What happens down here at the outlet at Kinston? What's the total reductions there with these scenarios? So we looked at Smithfield, Goldsboro, and Kinston. We kind of went down the model and the river. And what we found is that in Smithfield, there's virtually no reduction. And that's just because we have so little opportunity in that upper part of the basin. Goldsboro, which is further down, for combined practices, we saw about 4.4% peak flow reduction. And at Kenston, that increased to about a little over 5% there. And this would equate to a water surface elevation reduction of zero point 0.3 and zero point 0.4 feet. So we're not talking great big reductions here. It's pretty small drop in the water surface of the river at those points during these storms. And again, this was a Hurricane Matthew event that we're simulating on the Neuse River. So if we just look at, this is at Kenston, US Highway 70. Again, here's the river with the bridge going across. They have a floodplain channel. And then the water is very spread out. This is the kind of 100-year storm. So even if I reduce the water surface by a full foot, I'm still way out onto the floodplain. Because again, when we're in these 25, 50, 100-year events, water comes out of the banks of the waterway onto the floodplain. That's kind of the natural way floodplains work, that we have a channel and water spreads out. So again, we're not talking about reducing the area flooding a lot, even with major implementation. We're talking about just lowering the water levels. So not to be too discouraging, because we did look at the damage reductions in Kenston and Goldsboro for the different return interval storms, and we found reasonable reductions, anywhere from 7% on up to 21% reduction in damages, just by that kind of lowering the water level a little bit, and the 50-year storm showing the greatest potential for those reductions. So we looked at water quality benefits as well, and Dr. Kirky Fox, he developed SWOT models for both Bayer and Nahunta, and he simulated the reductions from the reforestation and the water and the wetlands. He did not look at water farming, although they're likely to give some benefits. What he found is greater than 15% reductions in total nitrogen and total phosphorus for Bear Creek, where we had a lot of wetland opportunity and some reforestation. Little River, however, with only about 6% conversion of that to mostly forest, we did see significant reductions in total nitrogen and total phosphorus of 12% and 17% respectively. So even just fairly modest changes to reforestation in the upper basins could give us significant or substantial reductions, notable reductions in those nutrients. So we look, here's our three basins: Nahunta, Bear in the center, and Little River. And up to down, we have total nitrogen reductions, total phosphorus, and sediment. So you can see that the combined approaches, for example, here, sediment, reaching 20 and 30% reductions with wetlands and reforestation in Bear Creek, good reductions in Nahunta up to 16%, and very good reductions in Bear Creek because of those kind of wetlands, and even some reductions again in nutrients for Little River. So that was encouraging work. We looked at the nitrogen only, the credits that NCDEQ awards for their nutrient crediting, nitrogen crediting program. We looked at the 30-year credit that would be applied to those three watersheds. And with the combined wetland and water farming in these three watersheds, we found that that credit would cover about 23% of the construction cost of the practices. So that was very positive, that there is a water quality benefit that would offset some of the investment in the natural infrastructure. We did a variety of other economic analyses, working with a number of our partners from the NCSU Forestry Program through UNC Chapel Hill and the Soil and Water Conservation Foundation. Looking at leasing and purchasing options. Again, I showed you some of the we looked at direct cost to implement the practices. We looked at spending pathways. If you did spend that money on the natural infrastructure, where does that money go for contracting and monitoring of these sites? We looked at damage reductions. I showed you that already, and water quality benefits. I showed you some of that. And we also looked at kind of some of the not only direct economic impacts, but some of the indirect multipliers of where you put money out into the economy and it has a sort of ripple effect. And so this is just kind of a lot on this slide. I'm just going to break it down slowly. What we see here is the total area of opportunity for the practices in the Middle Neuse with reforestation, water farming, and wetland. We look at the cost of millions of dollars of these practices. So we're looking at $726 million to implement it. We see the cost per acre foot per acre of the practices, with wetlands being much higher than the other two practices. However, the water storage potential of wetlands is 3 times greater than water farming and much, much greater than reforestation. We see the jobs that would be created by implementing this, over 1,600 jobs. However, the total employment effects could be almost 9,000 jobs because of that kind of indirect multiplier effect that is very substantial. And even though we spend the $726 million, this would be a economic return of 791 million. So basically every dollar I put out in the economy to build these, to implement these, I would kind of get that back through spending that occurs with the construction of these practices, which all our multiplier effects were over double for the different practices, a little bit higher for the wetland and water farming. This was based on in-plan modeling that was done by UNC Chapel Hill, by a number of our partners. And so there would be definitely some spillover economic effects of this natural infrastructure. So in summary, the natural infrastructure has the potential to reduce downstream flooding. Opportunities are best on lower slopes where there's less development. Peak flow reductions are spatially variable and depends on kind of the location of where you place that natural infrastructure and the density of that, and also where you're kind of looking to gauge your flood reduction benefit. Practices have to be sized for large events. If that's what we're trying to mitigate, we need to size the water storage elements to be able to kind of reduce peak flows from large events. Peak flow reductions are smallest on the tributaries more so than on the main river segment. It's going to be very difficult to try to eliminate flooding on the main river because that's the natural process, is that floodplains flood. That's why they're named floodplains, and it's really critical we continue to get people out of harm's way and kind of really accept that development in floodplains is not a good approach. The flood storage wetlands provide the greatest benefit, followed by water farming and then reforestation. And the cost of implementation is substantial. However, there are regional direct economic impacts that will be realized from that investment, and the indirect opportunities are even more than double of that through employment and economic impacts. Here's a website on our Sea Grant, North Carolina Sea Grant page that has some of our work, not just what I've presented, but other work we've done up in Windsor and other areas on natural infrastructure. And I want to point out we just recently had 2 papers published on our Neuse Basin research, and I'm happy to send the links to those, one in water and one in ecological engineering, I believe, Journal of Ecological Engineering. So I'm happy to share those with you as well. And that's all I have, so we can open it up for questions now.
Okay, thanks so much, Dr. Dahl. I do have a few questions here. I'm going to start from the top. So, Katie wants to know, for the project where road crossings were removed and there were buyouts, what was the total project cost? It's a two-part question, so I'll just stop with that question, Dr. Dahl.
Okay, hold on. Say, I was trying to get to the chat window too, and I'm not good at doing. Somehow, every time you move around, you lose your chat. Okay, here you go. I see it now.
Okay.
Okay, so Katie Blaze,
Uh-huh.
All right, so for the project where road crossing, the project cost was estimated around $30 million. We did not do any other economic analysis on that, Katie. So good to hear from you, Katie. She's one of our former students here from BAE. So we did do an estimate of cost. I hope to do some community work in Big Ditch area of Goldsboro, working with the planning and engineering staff. I've presented this work to them, and to be able to see what kind of buy-in we could get from the neighborhood. They have some concern about eliminating crossings, but I think they would see the benefits if that area could be converted to park, greenway, and stream restoration. So we'd like to do some work. And I think there would definitely be some gains because there's actually abandoned houses, flooded houses, and that really doesn't do anything for the value of your home next door, even if you're not in the floodplain. So, all right, I see a question from Tom Garrow. For reforestation, it would take several years for the trees to grow enough to make a meaningful impact on evapotranspiration and add vegetation roughness to the landscape. What length of time did the model estimate it take for reforestation effects to kick in? Good question, Tom. We recognize that there's probably 20 years or more before you're going to really get a kind of full canopy to get those benefits of that. And so we modeled it, assumed a 30-year stand of timber on that. And that was more of a theoretical scenario to just kind of test, putting it out there, what would be the reduction. We know that that was not a kind of actualized scenario for Stony Creek, or, and that we have to assume this is an investment in those trees and the future outcome. It's not immediate. So a very good point with that. I will mention we're currently looking to identify demonstration sites for this work. And with the reforestation, we're going to be not just looking at the planting, but also adding the water storage element to reforestation. So just like berming the farmland, to berm the reforestation area, and kind of look at impact to seedling trees versus mature trees, because it's what I understand is the mature trees could take one to several days of flooding. As long as that water drains out, it'd be okay, but the seedlings are more vulnerable. So again, it may be that if you planted an area, if we find too much impact, you would not be able to, you'd have to keep your system open until those trees were large enough to be able to endure that temporary flooding. I will mention we did some modeling to see how long do you have to hold this water. And in general, we find it's at least 1 day and could be up to as much as 4 days that the water needs to be held to be able to really achieve the reductions that you're looking for. And it's very much determinant on the position of that infrastructure within the river basin or the kind of sub-basin point where, again, you're trying to reduce flooding. Okay, other questions. Fred Tarver. Hey, Fred. Appears that the Little River drainage identified north of Highway 64 is the drainage for Raleigh's proposed water supply reservoir. Yes. And in fact, we even did some modeling of that kind of area, looking at dry detention as well as other dry detention. So you're correct. And we considered that reservoir kind of planning in some of our modeling work. I didn't present everything that we've done. Some of the dry detentions mentioned in our journal paper and our study papers. There's some links to our work on the collaboratory page. I can share other links with folks after. From Al. Yes, I agree. Reforestation is a solution, but for the long-term planning. Okay. Thank you for that comment. Michelle has sent some links here. Okay, from Fred Royal, I assume. On the benefit side, did you look at flood damage reductions to crops or structures? So, what we considered with the crops is that we did workshops for farmers where we kind of laid out there, hey, we're looking at this idea of stormwater on farms and converting some farm area to wetlands. Well, how do you feel about that? Would you be open to that? They were then asked how many acres would they enroll in a program. And believe it or not, we got over 1,000 acres, and this group of farmers volunteered that they said they'd be willing to consider. And the reality is that when we get these really big events, they are having damaged crops. And even if the crop is not lost, they find that they cannot get back into the field to harvest it. So they see an impact. So they viewed this as that if they would be financially compensated, that this could be a more secure option for them, that they'd enroll these kind of areas that tend to get really wet and allow water to be stored, but they'd be paid for a leasing option, and they liked a 30-year lease upfront payment preferred, and then they would be paid for their crop damage. So that was the way we considered that. As far as structures, the only structures we looked at with that damage reduction I showed was everything that's in FIMAN, NC FIMAN program. So in other words, that gives you the number of structures at each water level, what's inundated and what's the damage cost. So all that, I didn't mention that. That's all based on the FIMAN data sets that North Carolina Emergency Management has on their website. And if you just search NC FIMAN, FIMAN, you will find that website.
Dr. Dahl,
Yes,
I think we skipped one for Larry. Did you want me to read that, or did you kind of want me to run?
sure.
Oh, okay.
Yeah,
So
sorry,
Larry,
Larry.
no, that's okay. Larry asked, does hydrology model incorporate effects of force, evapotranspiration, and rainfall capture or in interception?
We did not look at evapotranspiration because we're not talking about changing every day. We get a half inch, inch of rain. These systems are meant to be open and those areas operate like normal. And then they would be closed, like have whatever kind of gate valve or weir would be closed off ahead of a big storm event. So you want the system empty, and then you close it off, and so you've got all your storage there. So it's not about kind of everyday rainfall. Again, it's about big events. That's what we were kind of modeling on. Now that with our research coming up in demonstration sites, we're going to look at a lot of different aspects of this, including water quality, which may get into drain modeling, which would consider evapotranspiration as well, nutrient uptakes and all of that. What was the second half of that question, Michelle? I'm not seeing that.
It was just that one question.
Okay, did I cover it then?
I think we did. Yep. And I think we're down now to Al. Um,
Okay, I think I answered Al. Oh, wait,
okay.
wait.
Okay.
Oh, wait, he says, have we looked into structure resizing? I remember on the big ditch, there was a railroad. Yes, all that. So 7 of those crossings were uh, upgraded. So bigger pipes, bigger bridges, raising the deck elevation of bridges. So that work on big ditch included structures. Now we have also done a lot of work with structures on the Neuse, and we found minimal benefit, although except for in Smithfield at the 301 and I-95. And in fact, DOT is doing some more work on that. We've done a lot of work for DOT. Less benefit for the bridges along Goldsboro and the Neuse for like millions of dollars for that. You would only have, a few inches of reduction. We did a lot of modeling on other tributaries in Kinston and Smithfield, and similar to Goldsboro, you can get reductions by addressing structures, but also increasing floodway is positive. So it's that kind of combination. You have to do gray infrastructure with green. So yes, you're correct. There are some railroad uh, structures that are the worst. The big jump I had in Big Ditch at the top, that's a railroad culvert. So thank you for pointing that out again. All right. Boris Schulman, how much time evolves before financial benefits are occurring? Good question. I cannot remember the time frame for the M-Plan modeling. I would have to ask my colleagues at UNC Chapel Hill who did that or open up that report, but I don't think it was a long, long time. I don't know the period, but that is a good question. And I can, if you email me, I can follow up on that. I apologize. I don't know the answer. I don't know if anybody's on the call or the webinar from Chapel Hill that worked on that. John Danford. When identifying potential land for these improvements, was ownership considered? In lieu of public ownership, conservation easements could be a resource to negotiate with private owners. We did not. We did not look at parcel property, anything like that. We just looked at where, excluding areas with roads, if there's a lagoon, a hog farm, those slopes, the soils, we did all that. We did not, in fact, I try not to zoom in to show too much detail so somebody doesn't say that's my farm and get upset with that. Although I realize with Stony Creek, it could be pretty, easily found with that. So, yes, easements would be needed, and the Land and Water Fund has just released that $15 million in funding to try to get some practices on the ground. So I expect some of these mitigation banking firms to start talking to landowners about these potential ideas and maybe getting some of them on the ground. And agreements and payments would be required. You're not going to do this without investment and compensation. All right, Victoria Carter, in your experience, are there any natural solutions you have found that is beneficial for very flat lands and parts of North Carolina? Well, like already implemented, we have one of my co-researchers, colleagues here at NC State. He's been monitoring some farm ponds and actually found very substantial flood reduction benefits in that. Now, he's not looked at great big storms in their monitoring period, but they definitely have good peak flow reduction. So we're going to be looking at some of that kind of pond sizing, because one of the things the farmers mentioned is that if these systems could also include some water storage element they could use for irrigation during drought times, that would be a big incentive for them. So I think we need to design systems to work across the spectrum of flows from drought. That's where they need maybe some pond area they could irrigate from. During normal regular flows, if the wetland element, there's a treatment element because that's when we care about water quality, and then that we have a storage element during the very big events. So we need to consider, it's going to be with climate change, we're going to have less normal weather, we're going to the more extremes. So we need to design the systems across that range of conditions, and that's what we're hoping to achieve with our demonstration sites, if we can kind of find the sites and get funding for that. uh, Victoria Carter. Okay, that we answered. Christine Farrell, do you have plans to repeat the study further east in North Carolina or in other basins? Not right now. My plate's pretty full, and I think we're at the point where we feel doing some demonstration sites is warranted. That we've done a lot of the modeling, kind of geospatial work, and we want to get some things on the ground and kind of really validate the way they're constructed, the management, and kind of measure the quantify quality and quality water aspects of that. Hey, Larry Sneeden, good to hear from you. I know Larry. Have you looked at NRCS wetland restoration program? Combines reforestation and wetland creation with significant flow reduction and construction costs in the range of $1,000 to $4,000 per acre. I have not considered that program specifically with this. And yes, so restoration and creation would be good. Again, if flood mitigation is a target, it must have that storage component. So again, our wetlands were 10% as big as their drainage area, and drainage area were at least 35 acres or above. So if you're working in an area where you got a 1 acre drainage area and you're putting a wetland, you're not going to see the same benefits. Or if that wetland is tiny compared to the watershed, you don't have the same benefits. So it's really critical about locating it to have a significant watershed and to size it appropriately. So I don't know how much I can stress those two things. To get the type of benefits we showed, that is what's critical. I know some of the wetlands are very just capturing a small amount of water on that farm. Those are great because water quality is really important, and smaller storms you could maybe affect that. All right, Amin. Hey, Amin. A lot of my friends on here and colleagues. Are you aware of any studies that address flooding and implementation of natural infrastructure or green infrastructure in highly urban watersheds such as Walnut Creek? Well, lots of green infrastructure. Again, there's it really depends on where they're located. I would say when you're, for example, down in Wilmington, what's the big wetland there? That's anybody know the big wetland they put in Wilmington? Now that's, in an urban area, and that's sized in a way that it's providing a really big park for people. It's given documented water quality benefits, but that kind of structure may be something that's also providing flood mitigation benefits as well. I think that, we've been looking, very much on water quality, that the kind of transition is that a focus is on water quantity, to also look at that and how we can modify some of these structures, even in urban areas, to provide some benefits to flood mitigation. Charles Riley, are you aware, all right, has your team worked on smaller natural infrastructure features for urban and suburban sites? Not so much. Our, Dr. Hunt, Bill Hunt here, his team works more on stormwater systems, and they're doing a study they have done some looking at that. So maybe we can kind of tap them for a future webinar to kind of talk about, they've looked at more of resilience of stormwater infrastructure to extreme, climate change aspects. So that would be a good question for them. Again, we've only looked at the stream restoration and the crossings of those streams. Other than, Stony Creek was the scenario with storing water above the urban area. That's a scenario that doesn't exist everywhere. We have ag land above the city. And sand filters meet regulatory requirements, but often become forested because I'm not sure, I don't think you meant that word, the vacuum of sand with no vegetation. So yeah, again, that would be a really small area, a sand filter. That's kind of, again, to have real impacts, you have to affect a pretty large portion of the watershed. For instance, for Bear Creek, we affected 20% of that watershed with natural infrastructure, and we got about a 20% reduction. So if that sand filter is like 0.01% of the drainage of the whole watershed where you're concerned about flooding, that's going to be very small. Michelle Sensmore. Okay. Oh, thank you, Sarah. McCray Park, and McCray Park. Thank you. That's the big wetland. And Kevin Boyer, Wade Park. Thank you. Everybody's chiming in on that. Al, again, all basins in the study are in the coastal plain, flat basins. Have we looked at any case studies where the basins are in the mountain or western Piedmont? We have not modeled that. No. So, cannot comment on that. And then Clay Bark. Hey, Clay, good to hear from you. Any fact sheets or materials available for distribution to farmers and owners? That's a wonderful poke at us, Clay, because we have a draft fact sheet already, and it's gone through a couple rounds, and I need to kind of finalize some of the changes and get that out, because really critical that we be able to show them what this would look like. So that been a little busy, but we have that in the works, and you just email me again, because when I get those types of requests, that'll kind of get me on finish our team finishing that up. So I appreciate that. I recognize that's a need. All right, I don't see any more questions in chat. Is there anybody I skipped or anything I didn't answer clearly? I think we're about out of time at 12:01.
I think we pretty much got all of them, Barbara. Dr. Dahl, thank you so much for taking your time out to present this for your presentation. And Dr. Dahl, will you be willing to share your presentation with us so we can post it on our website?
Sure.
Okay.
And yeah, so I can send some other links too for the reports and stuff as well.
Okay, wonderful. So when she sends me all that information, we'll get this uploaded on a website for you guys can have for future reference. And again, thank you guys so much for attending these webinars. They've become very successful, and they would not be successful without you guys. So thank you, thank you, thank you. Please do not forget about our upcoming webinar with Dr. Matthew Jones on July 20th. I'll be flooding your emails again with the marketing materials regarding that. And if that's it, again, thank you so much, Dr. Dahl, for your time. It's greatly appreciated. And you guys have a wonderful rest of the day. I'll drop the link again if you guys didn't get it previously. So I'll drop it here momentarily. And you guys have a wonderful rest of the day. Thank you so much.
Michelle, what was the total count on attendance? Did you see that? I didn't see the number. I just wanted to check.
Yes, ma'am. It was 203.
Okay, great.
Yes, yes, it sure was. So it's a pretty good attendance. We had a total of 393. So usually we have anywhere between 70 to 75% in attendance from the registration. So it's kind of low a little time, but it's still for 203 people to take time out. Yeah, that was a really good attendance. So
Great. Yeah, I just wanted to kind of get that number. We keep that in our reporting. So,
yeah, yeah. So
and
that is
I will
good.
send you the presentation and I'll send some links that you could add to that.
Okay, sounds great. Well, thank you again. I really appreciate it. So
You're welcome.
my husband's in the background to my tail, Dr. Dahl.
Oh, okay.
Stephen Smithfield said hello.
Oh, tell him hello back.
Well, you have a wonderful rest of the day.
All right, you too.
All right, bye bye.
When I see Larry's comment. Thanks, Larry. Yeah.